Right, welcome back. So let's recall where we were last time. So throughout today, vector space V is always going to be this two-dimensional vector space with basis 1 and x. And grading is given as follows. So grading of 1 has degree 1, and grading of x will have degree minus 1. So the example that we were looking at looks like this. So we have a chain complex where outside of C1 and C2 they're all 0. And so let's call this map D1, D2. And we define C1 to be tensor product with V itself. But we are going to do a grading shift by 1 for this. Define this to be V, but also grading shift by 2. So this is Q of 1 tensor 1, 1 tensor x, x tensor 1, x tensor x. And this is just Q of 1x. But the gradings are shifted. So let's write down the gradings. So gradings. So this is the homological grading. So let's denote that by I. So this is quantum grading. Let's denote that by J. So these are the bases. I have 6 bases for this whole chain complex. So let's write them out. 1x, 1 tensor 1, 1 tensor x, x tensor 1, x tensor x. So these are all of them. And as I said before, so we are getting into this bi-graded vector spaces. That means it has 2 grading. One comes from homological grading and one comes from quantum grading. So 1, which is here, has homological grading 2. X also has homological grading 2. But for the quantum grading, so X usually has grading minus 1, but we shift it by 2. So I have, so let's write this as minus 1 plus 2, which is equal to 1. 1 usually has grading 1, but I'm going to shift it by 2. So this grading is 3. And you follow the same thing with the other guy too. So 1 tensor 1 and all of these guys, they are in C1. So they have homological grading 1. For the quantum grading, so for 1 tensor 1, we will be adding grading 1, so 1 plus 1. But we have the shift by 1, so I have 1, which is equal to 3. For 1 tensor x, I have 1 minus 1, but shift by 1, so this is equal to 1. I have minus 1 plus 1 plus 1, which is 1. And minus 1 plus 1, which is minus 1. So these are the gradings. So at this stage, so this is a chain complex. So in our case, it's just C1 plus C2. But each C1 and C2, they break it into these for C1, they break it into this all of these vector spaces, and C2 they break into these vector spaces with respect to this quantum grading. So I can write C as this bi-graded vector space, where for the C1, they break it into quantum grading 3, 1, and minus 1. So I'll write it as C1 minus 1 plus C1 C1 1 plus C1 3. So this corresponds to C1. For C2, I have these two quantum gratings, 3 and 1. So I have C2 3 plus C2 1. So C1 minus 1 corresponds to this. So it has dimension 1. C1 1 corresponds to this. So it has dimension 2. C1 3 corresponds to this. So it has dimension 1 and so on. So this is how you get bigraded vector space given this kind of chain complex. So now what I want to do is I haven't really talked about this differentials yet. So I want to define what they are. But the point that I want to make is that I want to make sure that if I fix a quantum grating, I want that to be just ordinary chain complexes that we talked about before. So what do I mean by that? So if you look at this, there are only 3 quantum gratings, 3 and 1 and minus 1. So if I fix a quantum grating, let's say j is equal to 3. So I'm going to look at this, but I'm going to forget about all the other quantum gratings. I'm just going to focus on quantum grating equal to 3. So I have 0 to C1 3 to C2 3. Okay, so C1 3, remember, that was the one that corresponds to Q of 1 tensor 1. And C2 3 should correspond to this fellow over here. Okay, and if I focus on j is equal to 1, I have 0 C of 1 1, C of 2 1, so on, and C1 1 now corresponds to Q of 1x, x tensor 1. C2 1 corresponds to Q of x. And when you focus on j is equal to minus 1, this corresponds to Q of xx. And C2 minus 1, there's nothing there, so this is 0. Okay. So what I want to do is that I would like to define a map, D1 and D2, so that when you just focus on each of the quantum gratings, it gives you a differential. In other words, in each of these stages, you want to make sure d squared is equal to 0. That's how I want to define these quantum gratings. So this is what I'll do. I'll define this 1 tensor 1 to get mapped to 1. So let's write that as 1 tensor 1. Let's map to 1. For here, I would like to define 1 tensor x goes to 1, and x tensor 1 just map to 1. And for this, I define x tensor x to get mapped to 0. Okay? And notice that if I define it like this, in order to define what D1 is, I just have to specify where all of these 4 bases are getting mapped to. So once I define like this, that defines what D1 has to be. So this is the idea of how we are going to define differentials. So let me write down this as a definition. A bigraded chain complex is a bigraded vector space with linear maps dij from Cij to Ci plus 1 comma j, so that if you compose 2 of them, So this is dij and d of I minus 1 comma j. You want this composition to be 0. Okay. So what this is saying is that you have this bigraded vector space, and once you fix a quantum grading, so this is where the quantum grading is equal to j, and you look at all these this chain of maps, and you want to make sure that whenever you compose 2 of them, it becomes the 0 map. So you're just doing one thing at a time. Any questions until here? So just like before, we can define homology of this bigraded vector space. So definition, the I comma jth homology group of the bigraded vector space complex is defined to be a kernel of dij modded up by image. So let's write this as h of I comma j of c. We define this to be kernel of dij modded up by image di minus 1 comma j. So you look at this. So we know that image is contained in the kernel, so we're just going to take the quotient, and that is going to be the homology. Okay, so let's do an example. So I want to compute ij homology group of this chain complex over here. Okay, so for instance, what is H2 3 of C? It is 0, right? So the kernel is everything. So Q1, they all get mapped to 0. But if you look at the image, it is everything also. Okay. So if you look at this point, this is going to be equal to 0. H13 of C, what is this going to be? Q1 tensor 1, right? So at this point, so what is this map? This map is called D13, right? And I have a map from one dimension of vector space to one dimension of vector space where a basis gets mapped to a basis. So what is the kernel? Kernel is 0. And image is 0 because you are looking at image from 0. So this is going to be 0 mod 0, which is equal to 0. H21 of C. Kernel is everything, but image is also everything, so it vanishes. H11 of C. So what is H11 of C? So that's here, D11. So map from 2-dimensional vector space to 1-dimensional vector space. And this gets mapped to X, and X tensor 1 gets mapped to X. So what is the kernel? That's right. Right. So you should really think of this as map from q squared to q, where 1 comma 0 is getting mapped to 1, and 0 comma 1 is getting mapped to 1. So 1 comma 0 would correspond to 1 tensor x, and x tensor 1 corresponds to 0 comma 1. These are just basis elements. So once you have this, it's clear that 1 comma minus 1 is in the kernel. So it's generated by single vector space. So, okay. So this should be q of 1 tensor x minus x tensor 1. Is this not clear, or are there any questions? What about this? 1 minus 1. X tensor x, right? Because everything goes to 0, so this would be q of x tensor x. On the other hand, h of 2 minus 1 of c, this is 0 because the complex itself is equal to 0. Right, so this is not needed anymore. So at this point, we can define a graded Euler characteristic. So I know we have been doing a lot of algebra. This is the last thing that I'll be defining. So after this, we are going to be good. We'll just be doing some examples. So this is the last thing that we have to learn. So graded Euler characteristic of a bi-graded chain complex. We define it as summation of ij. So we have two grading. The homological grading is used to alternate sign. Quantum grading, we're going to record it with q. And the additional thing that we'll be looking at is the dimension of hij of the complex. Okay? So let's go back to this example. So all of these guys have dimension 0. This is isomorphic to q, so this is dimension 1. This is also isomorphic to q, so this has dimension 1. Right? So using this fact, so let's try to compute the quantum grading, the graded Euler characteristic. So for this, I is equal to 1, so minus 1 to the 1. Quantum grading is 1, so I have q to the 1. And dimension of this homology, 1, 1 homology is equal to 1, so I multiply 1 for that term over there. Okay. For h1 minus 1, homology grading is 1, so I have minus 1 to the 1. And for the quantum grading, I have q to the minus 1. And dimension of that is also 1. So if you write this out, this is going to be equal to minus q inverse. So this will be Euler characteristic, graded Euler characteristic of this bi-graded chain complex. Okay. On the other hand, you can define this in a slightly different way. Maybe I should write that over here. So alternatively, we can define GR of C, which looks almost the same, ij, with minus 1 to the I, and q to the j. Instead of computing dimension of hij, you can put dimension of c of ij. Okay. So let's see what happens. So we have this has dimension 1. This has dimension 1. This has dimension 2. This has dimension 1. This has dimension 1. So let's see what happens for all of them. So homological grading 1, quantum 3, so minus 1 to the 1 q cubed with dimension 1, and minus 1 to the 2, and quantum grading 3 with dimension 1, and minus 1 to the 1 of q to the 1 plus minus 1 to the 2, q to the 1, and so I need 2 here, and I have minus 1 to the 1, q to the minus 1 with dimension 1. So if you add all of these up, I notice that these two cancel. I have 2 and 1 here, so it turns into minus q. I have a minus q to the inverse. So in fact, you get the same answer from here. So in general, yesterday I believe that for single graded chain complexes, you've seen that taking the Euler characteristic with homology and chain dimension of the chain complex itself, you've seen that it's the same thing. But it's just exactly the same proof implies that it's also true for the bi-graded chain complex. Okay, so great. So this is all I wanted to talk about with respect to algebra. So this is, I was supposed to finish this yesterday, but I wasn't able to do it. But are there any questions until here? So this is all you have to know before we get to the definition. All right. So this is our goal. So we are going to start with a link. We are going to find a diagram for this link. So let's call D a projection diagram. For L. And once you have this, what we are going to do is we're going to define this bi-graded chain complex, C of D. So this is going to be a bi-graded chain complex that comes from this diagram. And then we are going to take a homology of this. So H star star of D is going to be sum of Hij of D. So this is going to be kernel mod the image, and we are going to look at this homology over here, and we are going to call this Kovanov homology. Okay. So in order to do that, I have to tell you how do I define this, and I have to tell you what are the Dij maps so that you can take homology to compute the Kovanov homology. So this is what we are going to do next. And the key thing that you should keep in mind is the following things. So the first thing is that throughout this process, what you should make sure is that there were many choices that were involved. So especially here. So given a link, there are many ways to get this diagram. But as we've seen the first day, any of these diagrams are related by Reiter-Meister moves. So what you need to do is that this resulting thing does not depend on the choice of that diagram. So the first thing that you need to make sure is that if D and D prime are related by Reiter-Meister 1 and 2 and 3 moves, you want to show that H star star of D is isomorphic to star of D prime. So this is one thing that you need to make sure to get a not invariant. And second thing that we've been talking about was this actually categorifies Jones polynomial. So the second thing that we want to get is that from this not invariant over here, is it possible to recover the Jones polynomial that we've been talking about? And in order to get that, we'll be taking this graded Euler characteristic, CFD. And this is going to give us this unnormalized Jones polynomial of your knot. Okay. So this is another thing that you should keep in mind of. So we won't be able to show that this is in fact a not invariant, and also we won't be really proving this, but we'll kind of get an idea of why this has to be true. So this is more or less we'll see an example of how taking graded Euler characteristic of some complex in fact spits out the Jones polynomial. So this is what I would like to do today. So. So let's start with a diagram. So I would like to recall how we got the Jones polynomial. So from D, we have this hypercube, and each vertex of the hypercube you can think about it as an element of 0, 1 to the power of number of crossings in the diagram. Okay. For example, when we're looking at this half link, also remember when you have crossing like this, there were two ways to resolve it, either from north and south and west and east. North and south, we labeled with 0. So west and east, we labeled with 1. So for this, we have two crossings. So we'll be taking a state in 0, 1 to the power of 2. So there are 4 vertices. So you have 0, 0, 0, 1, 1, 0, and 0, 0, 1, 1. They're connected like this. And 0, 0 corresponds to resolving both of them with north and south. So the picture looks like this. And 0, 1 should look like this. And 1, 0 should look like this. And 1, 1 should look like this. Okay. The first thing that we did was we counted how many circles we had. So we had 2 circles here. So for this, we had q plus q inverse squared. And also for these circles, there are 2 of them, so we have q plus q inverse squared. There's only 1, so we have q plus q inverse. For this, we have q plus q inverse. Okay. And next, what did we do? We said I would like to multiply minus q to this factor. And with respect to the number of 1s that I have on alpha. So in this alpha, I don't have any 1s, so I don't multiply any minus q. But for this, I have 1, 1, so I will be multiplying minus q dd1. The same thing for here. I multiply minus q. For this, I have 2 1s. I'll be multiplying minus q squared. Okay. So the Kaufman bracket for this diagram was summation of all of these 4 factors. So let's write it as q to the 0, q plus q inverse squared, q dd minus q, q plus q inverse, minus q of q plus q inverse, minus q squared of q plus q inverse squared. So this was the Kaufman bracket, and in general, the equation was given as follows. You take a summation of alpha, which is contained in 0, 1 to the number of crossings, and you do minus q to the number of 1s in alpha, multiplied by q plus q inverse of number of circles in the states. Let's call that gamma alpha. Okay. So this is the formula. So instead of writing this over and over again, I'll call this R alpha. And number of circles in gamma alpha, I'll call this K alpha. Okay. So using this, the unnormalized Jones polynomial we can write it as j hat d of minus 1 of n minus times q of minus 2 n minus plus n plus of the Kaufman bracket. So remember, n plus I write this here. So n plus is number of positive crossings, and n minus is number of negative crossings for the link. So let's give orientations like this. So in this case, n plus is going to be equal to 0, and n minus is going to be equal to minus 2. And so I'm going to take that formula and multiply to this fellow over here. So minus 1 to the n minus times q dd minus plus n plus times summation of alpha of q dd r alpha times q plus q inverse of k alpha. And I'm going to put this fellow inside. So this turns into summation of alpha of minus 1 td and minus plus r alpha times q td minus 2n minus plus n plus r alpha times q plus q inverse k alpha. So this is how you get the Jones polynomial in general. This is how you systematically compute the Jones polynomial. So this was the Kaufman bracket of D, but the only difference, if you want to compute j hat of D, I'll be multiplying this extra term over here. So I'll be multiplying qtd minus 4. So qtd minus 4 plus qtd minus 4 plus qtd minus 4 and qtd minus 4 over here. This is how you get the Jones polynomial. Okay. So as I said before, our one goal was to associate a bigraded chain complex here. So that when I take the graded Euler characteristic, I want it to spit out these polynomials. This is what I want to do. Okay. So let's see if we can do this. So again, V is Q 1x, where 1 has gradient 1 and x has gradient minus 1. So let's look at this chain complex. So you have 0 everywhere. So C minus 1, C0, C1, 1. So let's say everything until here is 0. Everything here is 0 also. Let's define C0 to be equal to V. Okay? And also remember that the graded Euler characteristic is defined to be summation of ij, where minus 1 to the I, q to the j of dimension of c of I comma j. Or it can be also computed with h of ij. Okay. So if I want to compute this, what should I get? How would I compute this? So I'm defining this bigraded chain complex so that everything below C minus 1, they're all 0. Everything above C1, they're all 0. Only non-trivial thing is C0, and I want to define that to be V. So what would be the So what should I do next, for instance?
What are the grading on V?
Right. So grading on V. So write this as Q of x with Q of 1. So the grading on x is minus 1, and grading on 1 is plus 1. So right, so for this chain complex over here, this is Cij. All of them vanish except for C0, right? And C0 is V and it has these two quantum gradings. So I can write the C0 as C0 comma minus 1 plus C0 comma 1, where C0 minus 1 is Q of X and C0 1 is Q of 1. Okay, so this has dimension 1 and this has dimension 1. Okay, so if I want to compute this, even if I put an I with different number, they're all going to be 0 because the dimensions are all 0. So only thing that I care about when is I is equal to 0. So I have minus 1 to 0, which is 0. And so I'll be summing j of q to the j of dimension C0 comma j. So this is the case where I is equal to 0. So now I want to look at all the j's of dimension of C0j, but only thing that is non-trivial is minus 1 and 1. All the rest are all equal to 0, so this should be equal to q to the minus 1 plus q like this. Okay? So what happens if I change V into V tensor V? What is the graded Euler characteristic for that? It's squared, right? Because for V tensor V, V tensor V looks like Q of 1 tensor 1, 1 tensor X, X tensor 1, and X tensor X. So this has quantum grading 2, these has quantum grading 0, this has quantum grading minus 2. So you get, so if you write this out, you get q squared plus 2 plus q to the minus 2, so which is exactly square root of this, right? So in general, if you have v to the m, the resulting thing should be q to the inverse plus q to the m, like this. Okay? So now, let's generalize this slightly further. So instead of having everything on C0, so let's shift this. So let's say everything else is 0 except for Ci. So this is Ci plus 1, Ci plus 2, Ci minus 1. So everything else is 0. And let's say in Ci, I have v to the m. So if I want to compute this, what's the difference now? What is the difference? So let's assume all of them are 0 here. All of them are 0 here. And I'm assuming Ci has v to the m tensor product. Sorry, what?
The sign.
That's right, that's right. So before getting from here to here, we did minus 1 to the 0. The only difference is it just have to do minus 1 to the I power. So result for this should be equal to minus 1 to the ith power of q plus q inverse to the m. Okay, so the very last variation is this. So what happens if I shift the grading by k here? So everything is 0 there, but I just shift the grading by k. So for example, q of 1x, where you don't shift the grading, you have q1 plus q of x. So this has grading 1 and grading -1. If I shift the grading by 5, it's exactly the same vector space, but grading of this is now 6, and this is 4. Okay, so you take the exact same thing, but if I shift the grading by k, what does all the characters spit out? Sorry, what? Here? It's close. So something happens to Q, right? Right, but so this changes. This is shifted by k. So instead of this, I'll be just multiplying extra q to the k. Right? Because when this says grading 2, it was q squared, but if this turns into 7, then I'll be multiplying q to the 5 instead. So I'll be multiplying q to the k. Okay. So the idea is that you have all of these 0. If you have ci, where it looks like this is the polynomial that you get. And you take a graded Euler characteristic, okay? So having this in mind, so let's define a chain complex. From D, I'll be choosing a state, alpha. And from there, I'll be defining V alpha. V alpha is defined in this way. So I'll be taking tensor product of V k alpha times. Remember, k alpha is number of circles in the state. So for this it will be 2, for that it will be 1, for this it will be 2. And I'll be doing a grading shift, -2 minus 2 minus plus m plus r alpha. So these were number of crossings. M plus was positive, this was negative, and r alpha was number of ones that you see on the alpha. So let's see. So for 0, 0, V of 0, 0, I'll be doing V tensor V. So I'll just write it as V tensor V. Because I have 2 circles, I'll be doing a grading shift. For us, there are only, wait, should be just positive 2, sorry. So I'll be doing -4. And R alpha, there are no ones on the circle, so I'll be just doing -4 as a shift for this state over here. Okay? 2 circles, V tensor V. -2 m minus 1, which is -4. Okay, so let me just write this. -2 m minus plus n plus alpha. This is -4. This is equal to 0. This is equal to 0. There are no ones on the right. So add them all up. I put -4 on the right. Okay? Let's do this for 0, 1. So V of 0, 1. There's only one circle, so it's just V. For the grading shift, this is exactly the same thing, but I have 1, 1 in 0, 1. So I'll be just adding 1, right? So I have -3. The same thing for here, V of 1, 0 is V. I'll be adding 1, so it's just -3. At this stage, I have V, 1, 1. I have 2 circles, I'll be doing V tensor V. -2 n minus plus n plus, there's still -4, but I have 2 ones in alpha. So I'll be adding 2, so I'll be getting -2. So these are the chain complexes. So now I have to give grading to these. So for the grading, so the logical grading, is given by R alpha minus N minus. So it's number of ones that you see in alpha, and you're going to subtract by 2. So what's a different color? So for this, the homological grading is going to be 0, minus 2. So this will be minus 2, homological grading. For this, I have 1. I'm subtracting minus 2, so I have minus 1 as a homological grading. For this, again, same thing, 2 minus 1. Right, 1 minus 2, which is minus 1. And for this, the homological grading is going to be number 1 is 2, 2 minus 2, which is going to be equal to 0. Okay, so homological grading from left to right. So the point is, when you start here, when you move to the right ones, homological grading goes up by 1. And from here to right, it goes up by 1. So I have minus 2, minus 1, and 0. So this means that if I want to define a differential, I need to define a map from here to here and from here to here. So that's what I'm going to do next. But before we get there, I'd like to convince you that if I take the Euler characteristic of this complex, this will be splitting out this Jones polynomial over here. This is what I want to talk about next. And obviously, the quantum grading is coming from this grading over here. The grading coming from here, V. So whenever you see X, it has grading minus 1. Whenever you see 1, it has grading 1. And these indicate the grading shift for the quantum grading. So let's do this. So for the Euler characteristic, so for a graded Euler characteristic of this, what should it be? So hint is here. So this fellow over here, you should think of it as everything vanishes except I is minus 2, right? And I have V tensor V, and shift is given by minus 4. So the conclusion is we got from here, right? So I is equal to minus 2. Number of tensor products, I'm tensoring with 2 of them. And I've shifted by minus 4. So for this, I'll be getting minus 1 to the minus 2, Q plus Q inverse to the squared, and shifted by Q to the minus 4. Okay? Any questions? For this, V and minus 3, and homological grading is minus 1. So you should think of it as C of minus 1 is just this, and everything else is equal to 0. And again, if you look at that formula over there, I have minus 1 to the minus 1, Q plus Q inverse to the 1, multiplied by Q to the minus 3. Like this. Same thing goes for here too. So I have minus 1 to the minus 1, q plus q inverse 1, and q to the minus 3. Okay, and the very last thing over here is that I have V tensor V, which corresponds to m is equal to 2, and homological grading is equal to 0. So I have q plus q inverse squared, and I want to multiply q to the minus 2 with this. Okay, so this is what you get if you take the graded Euler characteristic. And now I want to compare this graded Euler characteristic with the Jones polynomial and see if they are the same thing. And so if you look at this, and if you look at this fellow over here, they spit out the same. Do they spit out the same thing? They spit out the same thing. And if you look at this, if you look at this fellow over here, they spit out the same thing. And if you look at this, and this fellow over here, they spit out the same thing, and this, and this, and they spit out the same thing. So this is not really a proof of why, if you take graded Euler characteristic, why does it give you the Jones polynomial? But hopefully you get the idea of how one can try to categorize one information to something more complicated. This is somehow the idea behind of this covalent homology. So I think I was being too ambitious. I was going to explain all these differentials, but I don't think I will. I don't think I have much time. So I think I'm going to take a little pause if you have any question. I'm going to move on to some applications of covalent homology instead of explaining the differentials and the technical detail. Maybe no, I don't think I will. Okay. So any questions? All right. So this homology was defined in 2000 by Kufanov, and so it took about 10 years to see if this is true. So this is a theorem of Kornheimer and Morovka. Which says the following thing. So the point is that this is a knot invariant. So if you have a knot, and if your knot is the unknot, if you compute this invariant that we talked about, they should spit out the same thing. Okay, so when I write this KH, there's a whole bigraded chain complex where you take the differential, so kernel mod the image, and the information that comes from the kernel mod image, we are going to call this KH. And the key thing was that So this follows from the fact that Kavanagh homologies are not invariant, and the remarkable thing is that in fact this is if and only if. So if you know how to compute Kavanagh homology of your knot, it tells you exactly if it's the unknot or not. But so this was upgraded to many different knots actually. So one thing is, one question that isn't resolved yet is that, again, the same thing. So since the Jones polynomials are not invariant, we know that if k is the unknot, we know that the Jones polynomial of your knot spits out the same thing as Jones polynomial of the unknot. And you can ask the same thing. You can ask if the converse of this fact is true. Let's write this as and this is a problem that we don't know how to solve yet. But on a slightly different direction, we know that if K is a trefoil, so if you have a knot that looks like this, we also know that this detects the trefoil. So Kavanagh homology of a knot is isomorphic to Kavanagh homology of a trefoil, if and only if the knot itself is a trefoil. So this is done by Mulvin and Civic in 2022. So you see that these results are quite recent, and so there are many variations of these results. So the other things include the figure 8 knot. So the same holds so K is the knot that looks like this. Or K has 1, 2, 3, 4, 1, 2, 3, 4, 5, and many more. There are many results that looks like this, so that which tells you this is the only knot that has that particular type of Kavanagh homology. So this is a quite interesting variant. One notable thing about this knot over here is that even though there are no other knots that have the same Kavanagh homology as this knot over here, but if you compute, so let's see if I can draw this first. So I think this is a knot. So let's see. You start here, you follow it around, and you come back. So this is an example of knot. So interesting property of this knot is that if you compute the Jones polynomial of this knot, and the Jones polynomial of this knot over here, they give you the same information. They have the exact same polynomial, but the point is that when you actually, so this is the same, but as I mentioned before, Kavanagh homology detects this T25 torus knot. So they are the same, but when you compute the Kavanagh homology of this knot versus Kavanagh homology of this knot over here, they are not equal. So somehow the effort of going through all these algebra and getting this new invariant in fact tells you slightly more, in fact a lot more information than the Jones polynomial itself. And one other thing that I want to mention is the following thing. So this sort of would have made more sense if we talked about differentials, but we haven't. So, but it's okay. One important property of Kavanagh homology is that if let's say I have this picture. Okay, so each slice, I'm going to think of it as R3. Okay, so each slice, imagine each slice is R3, and this whole thing is R3 times the interval. Okay, so as you go further down, so this is R3 times 0. In the middle, this is R3 times 1/2, and the last stage, think of it as R3 times 1. Okay. In R3, you can think of it embedding of a circle, which is we've been calling it a knot. So let's say I have a knot inside R3 times 0, and let's say also I have a knot in R3 times the interval. Okay. Suppose inside this fourth dimension, let's say there is a cobordism between them. In other words, let's say there is a surface that is co-bounded by these two circles. So cobordism can look something like this. So you could have some holes. Okay, so you have this interesting surface that is embedded inside this R3 times interval, where the very left, let's say I have K, and let's say in the very right, let's say I have K prime. Okay. So what happens with this Kavanagh homology is that this surface, let's call this sigma. This gives you a map between Kavanagh homology of K and Kavanagh homology of K prime. So which you can't really say anything when you're just talking about polynomial. We can't really talk about maps between polynomials, but now we have vector spaces, so it makes sense to talk about maps between vector spaces, but the information comes from cobordisms between them. So once you have this, then there is a linear map. Let's call it Kavanagh of sigma from Kavanagh of K to Kavanagh of K prime. Okay. So now this becomes an interesting thing. Let's say, so now before we were just interested in taking two knots and see if those two knots are the same or not. But let's say I want to bump up a dimension 1 higher. Now let's say I want to compare two-dimensional surfaces and see if those surfaces are same or not inside this fourth dimension. So I give you this red surface, and later you come to me and you present a different surface. Sigma prime, and we want to compare if the sigma and sigma prime is the same or not. Okay. So what we have to do is you compute this map and you compute sigma prime of this map and see if these two maps are the same or not. If those maps are different, we can conclude these surfaces are different. So we are going one-dimensional higher than what we were doing before. So I want to end my talk with this picture. So it might take some time to draw this, but let's see if I can do this. So this is a knot. There's a way to find two different surfaces that is bounded by this knot. So one surface comes from looking in this way. The other one comes from looking at surface from this way. I won't finish drawing it, but there is two different ways to draw a surface for the same knot. So those two surfaces, let's call this call this yellow surface sigma. Let's call this red surface sigma prime. And those two were surfaces that live inside three-dimensional space. So inside the three-dimensional space, it was easy to see if those two are different in 3 dimension. The fact that these two surfaces are different in 4 dimension was a question that remained for a long time, but it was recently solved. By using Kovanov homology, and I want to end my lectures here. Thank you. Maybe I should write who did this. So this was work of Hayden, Sungwon Kim, Maggie Miller, and myself, and 22. So it was recently. It wasn't clear that such surfaces existed in the 4th dimension, but this was the first example that was found recently, and it uses this Kovanov homology map. So, anyways, I'll end things here today. Thank you.